In this video, I'll look at the proof of Kepler's first law. What was Kepler's first law? Kepler's first law was the planets are moving around Sun in a plane, and in that plane it moves in an elliptical orbit. So I have already proved that the planets are moving around Sun in a planar plane. The motion of planets around Sun is planar. We have already proved this fact. We have seen how this comes from law of conservation of angular momentum. Now we are going to prove the fact that in that plane the planet takes an elliptical orbit. If you have Sun, then planet moves around Sun in a plane elliptical orbit. That's what we have to prove. That's what we have to prove. We saw that L is m r square theta dot, as is constant, right? Fine. So in a way we have to get the orbit of the planets. We have to find the orbit of the planet, and then we will show that this orbit is, and of course once we find the orbit we can clearly see whether it is ellipse or circle, right? So we will find the orbit first. Find the whole proof is all about finding the orbit of the planet, right? So we have already seen that angular momentum is conserved quantity, and we also know the fact that gravitational system is a conservative system. I hope we have discussed what is conservative. So gravitational forces, if you have only gravitational forces operating in a system, that kind of system is conservative system. We have already seen what is meant by the term called conservative, right? Conservative means in a system where only gravitational forces are acting, then the mechanical energy of that system is conserved, and that is true for planetary motion also. Mechanical energy of Sun plus planet system. If I take any planet and Sun as a system, then mechanical energy of system consisting of Sun and any planet is conserved. So what is mechanical energy? Let's call it E. That consists of PE and K. What is P? P is mass of that planet. We have a system of two particles, so P will be minus G, mass of Sun, say let's call it M, and the mass of planet, let's call it small m, upon R. And what is kinetic energy? Kinetic energy is mv square. I know what is V. For planets, V is velocity has got radial component also, and it has got a transverse component also. This is a component. If V is the velocity, then this is R. This is going to VR, radial direction. This is V theta. This is VR and V theta. Velocity can be split into VR and V theta. This is your VR. This is V theta. So V square is what? V dot V, R dot ER dot and ER and eta perpendicular to each other. That will be R dot square. Yes. So let's write this. R dot square. So that is alright. That means this quantity, potential energy plus kinetic energy, let's put it at the second place, plus half is E, and this is constant. And we have one more thing. What is that? L, which is, that is also constant. So for a planet, when the planet moves around sun, energy and angular momentum is constant. Now we can make use of this, and I can express theta dot in terms of L as this. So this will come as gmm by r, and 1 by 2 mr square. Theta dot is this is L square upon m square r4. All this can be written as plus L square upon 2mr square is E. So now we have two things coming up over here. One is your mr square theta dot is constant L, and the second constraint, when the planet moves around sun, then sum of these quantity is constant. They are the two constants of motion. So our target is what? Our target is to find the equation of trajectory, the equation of orbit, equation of path taken by the planet. So whenever you find equation of any path, what the equation is all about? Equation is just a relation between the coordinates which are used to describe the position of planet. If you use coordinate x and y, then equation of the planet moving in a certain orbit is nothing but relation which you have between x and y. And if you use r and theta, then you need to get a relation between r and theta. Either you have to express r in terms of theta or theta in terms of r, or a function of r and theta equals to constant, or you can express r and theta in terms of third variable, and that's called parameter. So our target is to get this relation which r and theta follows. That's the equation of orbit. That's the equation of orbit. And for this, you have to generate a differential equation r and theta. We have to generate differential equation r and theta. Then after solving the differential equation, I'll get this. Get your point? See, the orbit can be described by algebraic equation. This is circle. There is one more way of writing circle. I can write it as y. That's also a circle. This is the equation of circle in differential form, in the form of differential equation. It's an algebraic equation. So from here I will try to get differential equation of orbit, and then I will solve the differential equation of orbit, and I will get the equation of orbit, algebraic equation of orbit. Our purpose is to find algebraic equation of orbit. But first of all, from these two laws, law of conservation, linear momentum, and angular momentum, and law of conservation of energy, let's try to get differential equation of orbit first. So from here we get what? Theta dot. And what this theta dot is? Theta dot is d theta by dt, L upon mr square. And what is this? So dr by dt, r dot, which is dr by dt is what? It is equal to 2 by m E plus gmm by r minus under root. Is it now? So you got d theta by dt, you got dr by dt. Oh. So this is dr by dt, this is d theta by dt, and from here I will get dr by d theta, which is dr by dt upon d theta by dt, and this is what? E minus, plus upon L by mr square. or this can be written as, I can write this as L upon dr 2 by m E minus equals to d theta. So this is our differential equation and you have to integrate it. It is looking to be very complicated. It's not so complicated as you think. See, I'll make a change in the variable. Let's take 1 by r as u. Then minus 1 by r square dr will be d. Let's change the variable. Let's transform the variable. This is called transforming the variable. So that means this is, let me take L by m in the denominator. So this will be minus du, and if I take L by m in denominator, this will come over here and will become m by L, and if I take it inside, this will become what? 2m square by L square, but m square, this will cancel out, so it will become 2m by L square. I hope you understand this. So this is minus du and this is 2m by L square. So I take this 2m by L square inside, so this is 2me by L square plus 1 by r is u, so this becomes 2m by L square, so this becomes 2g m square L square u, and over here what do we have? We have here L square by 2m by L square multiplied over here will give you this. Getting a point? Yes? Okay. So, fine. Equals to d theta. Now, this is du, and this can be written as, see what I can write it, 2me by L square or minus twice of what? GMM into m yeah, yes, it's fine, u minus u square, and this can be now written as, see what I can write it, equals to d theta this is du two me by and plus g square m square by L4 minus g square m square by L4 plus twice of minus gm by L square, or this will be m4 in fact, into u plus u square equal to d theta. Just have patience, it will be nice thing which will come out. So this can be written as, see what I can write it. This is 2me by L square plus G square M square M4. This is M4 upon L4 whole square, and U plus minus GM square upon L square whole square. Yes, this is d theta. And now I integrate it. Instead of writing like this, you can simply write minus also. No issue. Right here, minus also. Okay. Plus some constant. And you know this under root is cos inverse x by a. So we use this. So a square x square dx by a square minus x square. So this is minus of cos inverse u minus upon under root 2me by L square plus G square M square M4 by L4, okay, equals to theta plus c, and this will come as u minus upon 2me by L square plus upon L4 under root equals to cos theta plus c. C is the constant of integration, or u, which is 1 by r, equals to, or let's say u minus u equals to gm square L square plus yeah, this minus is not required now. Minus, we already used this. This is minus. So this is equal to 2me by L square plus G square M square M4 by L4 cos theta plus c, or this is GM M square L square, and let's just say same thing common from here also, GM M square by L square. So 1 plus 2e L square upon G M square M cube cos theta plus c, and this is nothing but G M square upon L square 1 plus cos theta plus c, and this is u, which is 1 by r. So we have L square upon r equals to 1 plus cos theta plus c. And what is this? This is nothing but equation of ellipse. This is nothing but equation of ellipse, is it not? This is equation of ellipse. Is it clear? Okay, this is equation of ellipse, and eccentricity is 1 plus, it's extremely important, 2el square. This is eccentricity, and I'll prove it later on that energy of a planet moving in an elliptical orbit will always be negative. In fact, that is true for any bounded system. Every particle moving in a bounded system, the energy will be negative. So when E is less than 0, this eccentricity is less than 1. That means this is equation of ellipse. So the body moves in a elliptical orbit. In a plane, the body will be moving in a elliptical orbit. That's the proof. Not required, but if you read it, it's good. At least you should remember this part. That will help you somewhere. Right? So this is the equation of ellipse. So that is how we can prove it. Okay? I'll stop over here. Thank you.